Hello again. This is Math 2115 coming to you from the College of DuPage. The title of this lecture is Conditional Probability, Bayes Theorem, and Independent Events. And I remind you to be an active learner while watching this video. Conditional probability. By way of introduction, imagine a couple with two children, each of whom is equally likely to be a boy or a girl. Now suppose you are given additional information that one is a boy. What is the probability that the other child is a boy? Now here's a figure showing four equally likely combinations of gender for the children. You see it can be BB, BG, GB, and GG. You can imagine that the first letter refers to the older child and the second letter the younger, and thus the combination BG indicates the older child is a boy and the younger is a girl, and there is the picture. Now there are three combinations where one of the children is a boy, and in one of these three combinations the other child is also a boy. Given that you know one child is a boy, only these three combinations could be the case. So if you think of the set of these outcomes as a new sample space with three elements, all of which are equally likely, within the new sample space there is one combination where the other child is a boy. Thus it would be reasonable to say that the likelihood that the other child is a boy, given that at least one is a boy, is 1 out of 3. Given that the original sample space contained 4 outcomes, note that the following computation gives the same result. The probability at least one child is a boy and the other child is also a boy is 1 out of 4. And the probability at least one child is a boy is 3 out of 4. If we divide 1 out of 4 by 3 out of 4, we get 1 out of 3. A generalization of this observation forms the basis for the following definition. So this is the definition of conditional probability. Let A and B be events in a sample space S. If the probability of A does not equal to 0, because we can't have 0 on the denominator, then the conditional probability of B given A, and this is denoted as the probability of B given A. So that's saying that we're assuming that A is the case, and then what's the probability of B based on that information? This vertical bar is red. This whole thing is red. The conditional probability of B given A is, the probability of B given A is the probability of A intersect B divided by the probability of A. Let's compute a conditional probability using that definition. So in this problem, we're looking at a pair of fair die, meaning that they will have an equal probability of landing in any faces, and one of them is blue and one of them is gray, and these two are rolled together. What is the probability that the sum of the numbers showing face up is 8, given that both of the numbers are even? So let's look at the solution. The sample space is the space of all 36 outcomes obtained from rolling 2 dice and noting the numbers showing face up. We've done this a number of times in this course. So we denote by AB the outcome that the number showing face up on the blue die is A and the one on the gray die is B. You could think about that as being alphabetical order because B comes before G. That will help you remember that. So we let A be the event that both numbers are even, and B be the event that the sum of the numbers is 8. Then A is equal to the set of these outcomes, and B is the set of these outcomes. And A intersect B then is these outcomes. That's just set theory from those two. Because the dice are fair, all outcomes are equally likely. Probability of A is 9 over 36, probability of B is 5 over 36. And the probability of A intersect B is 3 over 36. So the probability of B given A is the probability of A intersect B divided by the probability of A. 3 over 36 divided by 9 over 36, 3 over 9, and that is 1 over 3. So we see how to do that calculation. We should note, and this is also important, that when both sides of the formula for conditional probability are multiplied by P of A formula for the probability of A intersect B is obtained. This is the general probability. The probability of A intersect B is the probability of B given A times the probability of A. Later on in this broader lecture, we will talk about independent events, and I'll ask you to recall this from then. And also, we could say what's the probability of A, and the probability of A also could be written, this is just doing algebra, as the probability of A intersect B divided by the probability of B given A. And this forms a basis for another part of the lecture that we will talk about called Bayes' theorem. Now, often drawing a picture can be very useful, and we can have a tree diagram. And so what we're going to do is we're going to represent this with a tree diagram in a bit. So suppose an urn, which is a jar, contains 5 blue and 7 gray balls. And let's suppose that 2 are chosen at random, one after another without replacement. That means you don't put the ball you picked back in. So we have a bunch of questions that were asked, and let's just deal with them in turn. So find the probability and illustrate with the tree diagram. The probability that both balls are blue, the probability that the first ball is blue and the second is not blue, the probability that the first ball is not blue and the second ball is blue, and the probability that neither ball is blue. That's a lot in part A, but let's talk about that. Okay, so we're going to let S be the sample space of all possible choices of 2 balls from the urn. Let B1 be the event that the first ball is blue, and let B2 be the event that the second ball is blue. And then B1 complement is the event that the first ball is not blue, and B2 complement is the event that the second ball is not blue. So part A, then, we're going to start working through these, and the first one, that the probability that both are blue. So because there are 12 balls, of which 5 are blue and 7 are gray, the probability that the first ball is blue is 5 out of 12. And the probability that the first ball is not blue is going to be, the probability of B1 complement is 7 out of 12. Now, if the first ball is blue, then the urn would contain 4 blue balls and 7 gray balls. So the probability of B2, given that B1 happened, is 4 out of 11. And the probability of B2 complement, given B1, is 7 out of 11. Think through these, make sure you understand all this. Where B2, the probability of B2 given B1 is the probability that the second ball is blue given the first ball is blue, and the probability B2 complement given B1 is the probability the second ball is not blue given the first ball is blue. So it follows from the formula that we talked about before that the probability of the intersection, the first 2 are blue, is going to be this, from the definition of conditional probability. It's the product of these 2 numbers. That's 20 over 132, and we could reduce that, but that is an answer for us, and it could be reduced to, I guess, actually you could reduce that several times. Let's just leave the number that way. And the probability the first ball is blue and the second is not blue is the probability of B1 intersecting B2 is the probability of the complement of B2 given B1 times the probability of B1, which is this product, which is 35 over 132. Similarly, if the first ball is not blue, then the urn would contain 5 balls, blue balls, and 6 gray balls. So the probability of the second ball being blue, given that the first ball was not blue, was 5 over 11, and the probability of the second ball not being blue, given that the first ball was not blue, is 6 over 11, where these probabilities are as we specified with the notation. It follows, then, the probability of the first ball not being blue and the second ball being blue is the product of these probabilities. That follows from the definition of conditional probabilities. It's these numbers, and it's 35 over 132. And the probability that neither is the probability of the intersections of the complements of B1 and B2, which is this by the definition of conditional probability, which is 42 over 132. And so we've answered part A. Now we're going to go and talk about what's the probability that the second ball is blue, and in turn at least one of the balls is blue. And then we're also going to say, if the experiment of choosing two balls from the urn is repeated many times over, what is the expected value of the number of blue balls? So we will answer all these questions in turn. But a tree diagram is a convenient way to help those. So you see, what we can do is we can draw this, and this actually simplifies the calculations quite a bit. So you see, the first ball is either blue or not blue, 5 out of 12 and 7 out of 12. And then the second ball is, and now we're at this site, so you see this state of nature says the first ball was blue, this says the first ball wasn't blue, so we can draw another branch where this is 4 out of 11, and this is 7 out of 11. And you see, this is the probability they're both blue. This is the probability that we're blue and not blue, not blue and blue, and not blue and not blue. And you see, each of these, we've structured this, so we are going to multiply probabilities to get this, and so we get these are our answers. So what we find then is, for part B, can occur in two mutually exclusive ways. Either the first ball is blue and the second one is also blue, or the first ball is gray and the second ball is blue. So you see, what we're going to do is, and by the way, all these are disjoint states of nature. And so what we're going to do is we're going to add the probability of the first one, which was the 20 out of 32, with the probability of the third one, which is 35 over 132, and we will get reduced 5 over 12. Thus, the probability that the second ball is blue is 5 over 12. And that's the same as the probability that the first ball is blue. And so what we can do is we can add those again together. So anyway, that's the answer that we get for B. For C, the union of any two events. So here is the probability of B1 union B2 is, and we knew this from an earlier lecture, probability of B1 minus the probability of B2 minus the probability of B intersect B1 intersect B2. This is the calculation. It's 15 out of 22. And so 15 out of 22 is approximately 68.2% that at least one of the balls is blue. This is an important example and very similar to some problems that I might ask you on a test someday. Here's part D then, and we're going through the same kind of calculation. Again, I repeated the diagram here because I think it really helps you. The event that neither ball is blue is the complement of the event that at least one of them is blue. So the probability of 0 blue balls is 1 minus the probability at least one ball is blue, and so that is going to be this calculation, which ends up being 7 over 22. The event that one ball is blue can occur in one of two mutually exclusive ways. Either the second ball is blue or the first one is not, or the first ball is blue and the second is not. And so in part A, we knew the probability of one blue ball was this. So by part A, we know that the probability of two blue balls are this. Therefore, the expected value of the number of blue balls is 0 times 0 blue balls plus 1 times probability of one blue ball plus 2 times this. And so when you calculate this expected value using the definition again from a previous lecture, you get 110 out of 132, or approximately 0.8. Now we turn our attention to Bayes' theorem, and this is by way of introduction. So suppose again that one urn contained 3 blue and 4 gray, but now a second urn contains 5 blue and 3 gray. A ball is selected by choosing one of the urns at random. either the first or the second urn, and then picking a ball at random from the urn. If the chosen ball is blue, what's the probability it came from the first urn? This problem can be solved by carefully interpreting all the information that we have. So, we're going to let A be the event that the chosen ball is blue. And we're going to let B1 be the event that the ball came from the first urn. And B2 be the event that the ball came from the second urn. So we know that because 3 of the 7 balls in urn 1 are blue, we know that the probability that we have event A given B1 is 3 out of 7, and the probability event A given B2 is 5 out of 8. And because the urns are equally likely to be chosen, the probability of B1 equals the probability of B2 is 1/2. Therefore, the probability of A intersect B1 is, by definition of the conditional probability, we have this. We multiply those and we have 3 over 7. And the probability of A intersect B2 is this, by the definition of conditional probability, and it is this when I multiply those two numbers. Now, A is the disjoint union of this set and this set, so by a probability axiom 3 that we had before, the probability of A is the sum of those, and that is going to end up being the sum of this plus the sum of this. Getting a common denominator, we have 59 divided by 112. Therefore, the probability of B1 given A is this, by the definition of the conditional probabilities. That is 3 over 14 divided by 59 over 112. It's this. And if I use a calculator, this is approximately 40.7%. Thus, if a chosen ball is blue, the probability is approximately 40.7% that it came from the first urn. Now, we generalize this idea to come up with a theorem that is called Bayes' theorem. And Thomas Bay was an 18th century Presbyterian minister, but he spent a lot of time being an amateur mathematician, and this is a very important theorem in the world of probability. Okay, and this is in fact is then a statement of Bayes' theorem. Suppose a sample space is a union of mutually disjoint sets, B1, B2, B3, ... all the way up to Bn. And suppose A is an event in the sample space, and both A and each Bk have non-zero probabilities for every integer k from 1 to n. Then the probability of Bk given A is the probability of, and this is A intersect Bk, but we write it this way, it is the probability of A given Bk times the probability of Bk, that's the definition of the intersection that we talked about, divided by all of these potential probabilities where we have the probability of A given B1 times B1 plus the probability of A given B2 times the probability of B2 all the way up to this. Now, we're going to be looking at this a great deal in the next section, and also often drawing a picture is useful in this regard. This is kind of a complicated formula to remember. And so, in lesson 26.2, we'll do more of this. But now, in closing, now more than ever, time is precious. Each day must count. Do the math. It'll make you strong. And now, more than ever, take care of yourself and of each other. May God bless you all. See you in 26.2.